All right, so today we continue with generalized eigenvectors and generalized eigenspaces, etc., and Jordan canonical forms. Of course, that's the overall topic. But first, we need to understand these generalizations of the concept of eigenvectors and eigenspaces. Okay, and let me remind you where we stopped last time. So we started proving theorem 7.3. So this was Theorem 7.3. Let me first remind the statement, and then I'll recall where we are currently in the proof of it. So the statement is that assume T is a linear operator on V, where V is a finite dimensional space, and assume that the characteristic polynomial of the linear operator T splits. Let also lambda 1 through lambda k be the distinct eigenvalues of T. Okay. Then we claim that for every x, a vector in the space V, we have that x is equal to v1 plus v2, etc., plus vk for some vectors vi in the corresponding generalized eigenspace k lambda I for all I between 1 and k. Okay. So the theorem is basically saying that the space V is the sum of the generalized eigenspaces corresponding to the distinct eigenvalues of T. Okay, and we started working towards a proof of this. So proof, and I recall the setup. So we are working on the induction step. So by induction on the dimension, let me write it explicitly, not the dimension, excuse me, the number of the distinct eigenvalues, right? So we're arguing by induction on k, so this k, the number of distinct eigenvalues. We're in the situation where we're assuming that k is greater than 1, and the result holds for less than k distinct eigenvalues. Okay, so this is the inductive assumption, and our task is to prove that then it holds for an operator T which has k distinct eigenvalues. Okay, so that's why we're assuming that T is a linear operator on V. We assume that it has k distinct eigenvalues. Right, k distinct eigenvalues. And we consider the characteristic polynomial. So we let f of T be the characteristic polynomial of T, right? We let M be the multiplicity of the last eigenvalue, lambda k. So remember, we're trying to somehow reduce the situation to the one where we can apply the inductive assumption. So we need to find some subspace with so that T restricted to the subspace has fewer eigenvalues, less than k. Okay. And so we let M be the multiplicity of lambda k, which means, because we're assuming that the characteristic polynomial splits of the operator T, so we have that the characteristic polynomial of T can be written as T minus lambda k to the power M times G of T, right? For some polynomial G of T, which is not divisible by T minus lambda k. So M, the multiplicity of lambda k, is the maximal degree, so that T minus lambda k to the power M divides F. the characteristic polynomial of T. Okay, and then we consider in the subspace W, we took it to be the range of the linear operator T minus lambda K times the identity to the power M. Okay, so this is a linear operator on V, because T is a linear operator on V. So makes sense to consider this subspace. And let me remind you what we have already proved about this subspace. So the idea will be to apply the inductive assumption to this subspace and then conclude. So we have already shown that W is a T invariant subspace, right? So we know this T invariant subspace. Then we had two claims. So claim one demonstrated that the linear operator T minus lambda Ki to the power M, it maps the corresponding generalized eigenspace K lambda I onto itself for all I less than K. This was claim one. And claim two, we have demonstrated that lambda K is not an eigenvalue of T restricted to W. Okay, so we have this part, and from the first part, we have that lambda I is an eigenvalue of TW for all I strictly less than K. Yeah, so we have these two claims that we demonstrated last time. So the conclusion of these two claims is that the distinct eigenvalues of T restricted to W are exactly given by all the lambdas except for the last one. So we have lambda 1, lambda 2, etc. through lambda K minus 1. Yeah. So this shows that T restricted to W has only K minus 1 eigenvalues. Yeah. So one less strictly less than K. So what this is telling us is that we can actually apply the inductive assumption to T restricted to W. Okay, so less than K distinct eigenvalues. Okay, and so now let's try to do that. So now we are going to apply the inductive assumption to TW and see how we can finally deduce the result from it. So we let X be a vector in V, arbitrary vector in V. Then we have that T minus lambda K times the identity operator I to the power M of X belongs to W. So this is simply by definition of W, right? Because look, W is the range of this linear operator, right? The range of the linear operator. So it means that if I take any vector and apply these same linear operators here to X, by definition, the resulting vector is in W. Okay, so we have this in W. Now, let K lambda I prime, so this is going to be a subset of W. So let this denote the generalized eigenspace of the linear operator T restriction to W corresponding to its eigenvalue lambda I. And we take this for I between 1 and K minus 1. Okay, so again, by our earlier conclusion, this part, we know that the distinct eigenvalues of T restricted to W are lambda 1 through lambda k minus 1. So it makes sense to consider the generalized eigenspaces of the linear operator TW corresponding to these eigenvalues of TW. Yeah. All right. Now let's use the induction hypothesis. So I'm going to switch to the next page. Let me pause for a second. Okay. So applying the induction hypothesis, to the linear operator TW, which has less than k, it only has k minus 1 distinct eigenvalues, right, by what we observed. So applying the induction hypothesis, we get that there exist some vectors Wi belonging to k lambda I prime, the corresponding eigenspace of TW, for I between 1 and k minus 1, such that we can write, so remember, we can write any vector in W as a sum of such Wi's. So in particular, we can write the vector T minus lambda k I to the power m of x. So again, remember, this is a vector in W. So we can write this as a sum of W1 through Wk minus 1. Right? So this is just the induction hypothesis applied to this particular vector that I have on the left. But we also have that k lambda I prime is a subset of k lambda I for I less than k. Yeah. So this is just by the definition of generalized eigenspaces. Remember, the generalized eigenspace k lambda I consists of all vectors. So in this case, we have all vectors in V, right? So this by definition is a set of all, let's say, V in V, such that T minus lambda k I, not lambda k, lambda I, excuse me. Yeah, so this is lambda I times the identity operator to some power p evaluated on V is equal to 0 for some p positive integer. And this is the same, but with respect to TW, right? So if I spell this out, this is going to consist of all vectors V in W, which is by definition again, right? So that TW minus lambda I to the power p of V is equal to 0 for some p and positive integer. And so from just unwinding these definitions, we see then that every vector that is in the left, in the set on the left, is also going to be in the set on the right, of course, because this is TW is just T restriction to W. So if this is equal to 0, the same is true for T, right? So this shows that we have this inclusion. Okay, but now given this inclusion, so since we have this, and additionally, we have that T minus lambda k I to the power m maps the space k lambda I onto itself. So this is by claim 1. And this holds for all I less than k. So this is, let me remark that this is by claim 1. Claim 1. Okay. So since we have this, so let me continue here. So we have that there exist vectors Vi in k lambda I such that T minus lambda k I to the power m of Vi is equal to Wi for all I less than k, right? Because this is operator is onto. So for each wi, we can pick some vector from the same subspace that gets mapped onto wi. So we let vi be a corresponding vector with that property because they're onto again, yeah. All right, but then what we get is that t minus lambda k I to the power m of x applied to x, yeah, this is going to be t minus lambda k I to the power m applied to v1 plus etc. plus t minus lambda k I to the power m applied to vk minus 1. All right. So here I'm just here I just replaced w's in this formula. So we have this part, right? That this vector can be expressed as the sum of wi's. So now I'm replacing each wi by the corresponding expression involving this mth power of the operator. So we get this equality. But then using linearity, excuse me, let me write it better. By linearity, we then have that t minus lambda k I to the power m applied to x minus, and then we have v1 plus v2, etc., plus vk minus 1. So applying the operator to this, we get that this is equal to 0. So I just look at the previous equation, use linearity of the operator t minus lambda k I to the power m, and moved all the things to one side. Yeah, this is just linearity. So this is equal to 0. But then, by definition, this is equivalent to saying that the vector vk equal to x minus v1 plus vk minus 1 belongs to the generalized eigenspace k lambda k. Right? Because we have, look, this is my vector. So I denote this by vk. This is a vector in v. And we have that applying this operator to some power, in this case, m power m, we get 0. So there exists a power which gives us 0. So this means that the vector vk is in the corresponding generalized eigenspace, right? But this means then that we have that x is equal to v1 plus v2, etc., plus vk, right? Simply because vk is given by this, so you can express x through this. So we get that x is given by the sum like this, and we have that each vi belongs to the corresponding generalized eigenspace k lambda I, and this holds for all I between 1 and k. And this concludes the proof of the theorem, because x, remember, x was an arbitrary vector in V. So we took x to be an arbitrary vector in V, and we have demonstrated that we can write it as a sum of the vectors vk. We just define vk here. It's not from, yes, this is the definition. So I can say it like let vk be this. Okay, so we let vk just be this vector, yeah. And what follows then, because of this equation, is that this vector is going to be in k lambda k. And that's exactly what we wanted, because now we have that x is the sum of these vectors. We already know for v1 through vk minus 1 that they're in the corresponding generalized eigenspaces from here. And vk defined like this is also in k lambda k. So this means that x's can be written as a sum of the v's, and each v is in the generalized eigenspace. Yeah. So this gives the required presentation for x, which I remind you was an arbitrary vector in V. So this means that V is the sum of the generalized eigenspaces corresponding to the distinct eigenvalues. So this gives us this concludes the proof of the theorem. Okay, so this gives us theorem 7.3. So the argument was a bit long, but again, I encourage you to review it. So the whole point was basically to find a subspace of with a smaller number of eigenvalues, so that we could apply the inductive assumption. And the space, we just remember we took it to be the range of the mth power of this operator. And then we had to use this to express an arbitrary vector x in V. All right. So any other questions about this proof? Okay. If not, let's continue. So we need to okay. So what we have demonstrated is that if the characteristic polynomial of an operator. Oh, there's a question in the chat. Let me see. How was k lambda I prime defined? So it was defined simply to be the generalized eigenspace. So it's written here. It's taken to be the generalized eigenspace of TW corresponding to the eigenvalue lambda I. Yeah. And so by definition, this is simply, this is literally this set. So I wrote it actually here in detail. This is just the definition of how we define generalized eigenspaces. So a set of all vectors V in W, yeah, which satisfy this condition for TW. All right, someone is raising a hand. Yes, please go ahead.
Oh, my bad. I didn't have a question.
Oh, okay. No worries. No worries. Okay. All right. So if there are no further questions about this part, let's see. So let's try to investigate further, understand further the properties of. So we want. Let me remind you what we are trying to do, maybe, yeah, globally. So we are trying to obtain an analog of the theorem we had for diagonalizable operators, which says that every diagonalizable operator, the corresponding space can be written as a direct sum of the eigenspaces of this operator. Now we want to obtain a similar statement but not necessarily for diagonalizable operators, but just for operators whose characteristic polynomial splits. And at the price of this generalization is replacing eigenspaces, usual eigenspaces, EI, by the generalized eigenspaces, K lambda I. Yeah. So that's what we are trying to do. Now, let me see. I want to ask you, I might have missed it, skipped it in class that we taught on Friday. Did we prove theorem 7.2? So let me just remind the statement. This is theorem 7.2. So assume that T is a linear operator on V, finite dimensional, and assume that the characteristic polynomial of T splits, the usual assumptions these days, yeah, and also suppose that lambda is an eigenvalue of T with multiplicity M. Then we have the following two claims. So the first one tells us the dimension, gives us a bound on the dimension of K lambda. So we know that it's going to be at most M. And the second part is that K lambda is the null space of the operator T minus lambda I to the power M. Okay, so okay, yeah. So okay, thanks. Yeah, someone is saying, I think we didn't do it in class, so let's prove it now. So as you see the statement, the content of the theorem, what it's telling us, it gives us a guaranteed bound on the power that we have to use in order to obtain the generalized eigenspace corresponding to the eigenvalue lambda. So, yeah. So as you see, remember the definition says, in the definition we are saying there exists some power P. so that when you apply this the corresponding power of this operator to a vector, you get 0, right? That was how we defined k lambda. So now here we get this additional guaranteed upper bound on the dimension of k lambda and also on the power that we have to use. And this guaranteed bound is given by the multiplicity of the operator. So let's check this. Let's prove this theorem. All right. So part A, let us take W to be k lambda. So fix the initial data is like in the statement of the theorem, is the assumption of the theorem. So we have a linear operator, characteristic polynomial splits, and we assume that lambda is an eigenvalue with multiplicity m. All right. So let W be the corresponding generalized eigenspace, and we let h of t be the characteristic polynomial of t. Of t restricted to W. All right. So by an earlier result, namely theorem 521, we know that the characteristic polynomial of the operator restricted to some invariant subspace divides the characteristic polynomial of t. So in this case, this tells us that h of t divides the characteristic polynomial of t, right? So in particular, we have that the characteristic polynomial h of t splits, because we're assuming that the characteristic polynomial of t itself splits. And so if some polynomial divides a splitting polynomial, that it also then it also splits, right? Because you can still write it as a product of linear monomials. Okay, so we have that h of t splits. But now, by theorem 7.1b, lambda is the only eigenvalue of TW, right? So recall, theorem 7.1b tells us that if we look at two different eigenvalues, then the restriction of the corresponding operator t minus lambda I to a different generalized eigenspace corresponding to a different eigenvalue, mu is 1-to-1. So in particular, so it's going to be 1-to-1. So from this, we can conclude that lambda is the only eigenvalue of t restricted to the eigenspace k lambda. And right, okay, so we have this, and so we can write that h of t, we can write it as minus 1 to the power d, t minus lambda to the power d, where we have that d is the dimension of W, and d is less or equal than m. Yeah, so remember, we know that this is how we get the initial, the main leading coefficient of the characteristic polynomial. If you look back at some of the basic properties of characteristic polynomials, we know that here you have minus 1 to some power, namely the power corresponding to the dimension of the subspace W in this case. Yeah, and so we get d is less or equal than m because m is the dimension of W. Okay, so this gives us part A, and for the part B, so now I want to show that this is the null space. So first of all, we have, okay, so we are trying to prove equality of two sets. So it means we have to show that inclusion in both directions, right? So first of all, we have that the null space of this linear operator is contained in k lambda. So this is immediate by definition of k lambda, of the generalized eigenspace k lambda. Because remember, k lambda simply says there exists some power for which this power gives us 0 on a vector. right? So in this case, we have power m, and since it's in the null space, so every vector in the null space, it's guaranteed that the mth power of this operator applied to x is 0. Yeah, so in particular, it is in k lambda. So the non-trivial direction is the opposite inclusion. So towards that, let us take w and h of t, the polynomial, be the same as in A. So w is k lambda and h of t is the characteristic polynomial of t restricted to it. Then we have that h of tw is equal to the 0 linear operator by the Cayley-Hamilton theorem. Right? Because h is the characteristic polynomial of tw. So we know that evaluating h on tw gives us the 0 linear operator. So this tells us that t minus lambda I to the power d of x is equal to 0 for all x in w, right? Because if it's the 0 linear operator, and we have the expression for h from part A, so it's here, and minus 1 to the power d doesn't play a role because we know that we get 0 here, right? So it means that this part has to be 0 for all x in w. But since the dimension, since the dimension d, which is the dimension of w, is less or equal than m, we then have, in particular, that k lambda is contained in the null space of t minus lambda I to the power m. Because already we see that already the dth power gives us 0 on every vector in k lambda, which is w, right? And d is less, we know that d is less or equal than m. So this gives us the, and if you already have 0, applying this operator again, if the power is actually strictly greater than m, than d, for example, you're just applying the remaining power to 0, right? So it stays 0 once it's 0. So we see that then taking it to the mth power also gives us 0. Like here, you can then replace d by m if wanted. Yeah. So this gives us the opposite inclusion. So this shows the equality of these two sets, k lambda and the null space of this to the power m. Okay, so this is theorem 7.2. And okay, so now let's return to our aim of showing a decomposition of an operator with splitting characteristic polynomial, the decomposition of the corresponding of the underlying space into the direct sum of generalized eigenspaces. So this is going to be the next result, theorem 7.4. Okay, so the situation is the same. T is a linear operator on V. V is finite dimensional, and the characteristic polynomial of T splits. All right, so the usual setup we have in this section. Let lambda 1 through lambda k be the distinct eigenvalues of T. Okay, with corresponding multiplicities which we denote as m1 through mk, right? So each one has multiplicity. Let's denote them m1 through mk. And for each I between 1 and k, we let beta I be an ordered basis for the corresponding generalized eigenspace k lambda I. Then we have the following: A, the intersection of any two of these, so beta I intersection beta j, is empty for I not equal to j. B, we have that beta, which we take to be the union of the beta I, so beta 1 through beta k, is an ordered basis for the whole space. So is an ordered basis for V. And finally, C, we have that the dimension of k lambda I is equal to mi for all I. So this is theorem 7.4. And at this point, you should compare it with the corresponding result. So we remember we had theorem. Okay, you probably don't remember it just by number, but the theorem was corresponding result for diagonalizable operators. So if you look back at that result, you will see that it's almost the same theorem. The only difference is that in theorem 5.9, the assumption we had on the operator was stronger. Now we only assuming that the characteristic polynomial of T splits. In theorem 5.9, we assume that the operator T is diagonalizable. And then the conclusion that we get now is also a bit weaker. So back then we had the same conclusion ABC as we have here, but the difference was that now we have k lambda I, and in that theorem we had the usual eigenspaces E lambda I. So this result 7.4, it is a generalization of theorem 5.9, where we relax the assumption on the linear operator T, and the conclusion also becomes a bit weaker. That's the price we have to pay for it. Yeah, we have to pass from usual generalized eigenspaces to the generalized ones. All right. So now let's try to prove this. Proof. Part A. So we have to show that which of these separate bases for the corresponding generalized eigenspaces are disjoint. Okay. So let's argue by contradiction. So well, or just suppose X is an element of the intersection like this. So assume that X belongs to beta I intersection beta j, which is in turn, of course, a subset of k lambda I intersection k lambda j for some I distinct from j. Yeah, so assume X belongs to the intersection of two bases. In particular, we must have that X is non-zero then, right? Because any vector in a basis is non-zero. And it belongs to a basis of a subspace, even to two of them. Okay. But then by theorem 7.1b, we have that the operator T minus lambda I is 1-to-1 on k lambda j. Right? So note we are using that lambda I and lambda j are two distinct eigenvalues. Therefore, we have that also T minus lambda I times the identity operator to the power P evaluated on X is not equal to 0 for any P positive integer. So we have this because X does not belong to the null space of T minus lambda I. Right? If we got that it was 0, we would conclude that it has to be in the null space, but the map is injective, 1-to-1 injective. So the null space is trivial, right? It has to be trivial, but we're assuming that X is not 0. So it cannot belong to the null space. All right. So we see that that this is not equal to 0 for any P, right? But this would give us a contradiction. So this contradicts that X belongs to k lambda I, which remember this was part of the assumption. If we assume that X belongs to the intersection of two bases, I and J, then it also belongs to the corresponding generalized eigenspaces. right? For which bases are contained in them. So x in particular belongs to k lambda I, but this is impossible because we have just proved that no matter what power you take, this is not 0 on x. So this gives a contradiction. So this shows that there's no vector that can belong to the intersection of two distinct bases for the generalized eigenspaces. All right, so this proves part A. Well, let's see, there's a question. Yes, exactly. The composition of injective functions is injective. Yeah. So it's not here, but hence it's also not. You can't get 0 if you keep iterating this, right? Yeah, exactly. So I guess I omitted this extra step. To be completely precise here, we have to say that we observe that this is not in the null space of just this operator, but from this it follows that it's also not in the null space of this operator to any power p. Yeah. Okay. So this is part A. Now let's look at part B. So we have to, now we want to show that if you take a basis for each of the generalized eigenspaces and take their union, we're going to get a basis for the whole space. Okay, so first let's show that this union generates the whole vector space V. So let X be any vector in V. But then by theorem 7.3 that we just proved, we have that for each I between 1 and k, there exists some vectors Vi belonging to k lambda I, such that we can write X as the sum of this. So we can write X equals to V1 to the sum V1 through Vk. All right. Okay, so we found some vectors Vi in each k lambda I. But also, each Vi is a linear combination of vectors in beta I, right? Because beta I is a basis for k lambda I, and Vi is a vector there. So it means that each Vi can be written as a linear combination of vectors in beta I. And so we have that X is a linear combination of linear combinations of vectors in beta I, right? But this means that in particular, X itself is a linear combination of vectors in beta, because beta is the union of the beta I's. And so we conclude that V is equal to the span of beta. We have shown that each vector in the space V can be written as linear combination of the vectors in beta. So we get that this is the span. So, but we also have to show that beta is in fact a basis. So we have to show that beta is linearly independent as well. So towards this purpose, let us take Q to be the cardinality of beta. So just the number of vectors, let Q denote the number of vectors in beta. A finite set, right? It's a finite union of finite sets. So let Q be the number. Then we have that the dimension of V is less or equal than Q, because we have just demonstrated that V is the span of beta. So the dimension of V is less or equal than Q. Let's show that it is actually Q, which then tells us that beta is indeed the basis for V. So for each I, we let di denote the dimension of the corresponding generalized eigenspace k lambda I. By theorem 7.2a, we have obtained a bound on this dimension, right? So we know that this dimension is bounded by the multiplicity mi. And so we have that Q, which is equal to the sum over all I from 1 to k di, right? So because di is the dimension of k lambda I, which is the same as the number of vectors in the basis beta I. But then Q, which is the union of this, and they are disjoint. So we have that Q is exactly the sum of the DIs. But this we can bound from above. So using theorem 7.2a, this is less or equal than the sum of the mi for I from 1 to k. Because each mi upper bounds the corresponding di, right? Okay, but this is equal to the dimension of v, right? Because this is the collection. This is the sum of the multiplicities. But remember that the sum of the multiplicities is just the sum of the powers of monomials appearing in the characteristic polynomial. And the degree of the characteristic polynomial is the dimension of the space. So we get that this is the dimension of V. And so hence, we have that Q is equal to the dimension of V. Because we have inequalities in both directions. On the one hand, the dimension of V is less or equal than Q. On the other hand, Q is less or equal than the dimension of V. So this means they're actually equal. So Q is equal to the dimension of V. And so this means that beta is a basis for V. Right? So this shows that beta is a basis for V. Because we have shown that it has the number of vectors in this set is the same as the dimension of V. And it's the span. All right. So this proves part B. Any questions about this argument? Okay, if not, let's just finish C. So C says that the dimension of each of these generalized eigenspaces is exactly the multiplicity mi. So let's check this. By part B. Let's see, there's a question. Does this mean that di is equal to mi? Yes, exactly. That's exactly what it means. So let's make sure that this is true. Yeah. So by B, we have that the sums are equal, right? So we know that di, the sum over all di over I from 1 to k, is equal to the sum over all mi, I from 1 to k. Right. So if you look at part B, since beta is the union of the bases from each subspace, so we have that we get that the sums are equal. Yeah. From well, what we just did in, like, if you look at this inequalities, what we just did in B, the sums are equal, and moreover, wait, let's see, would this be true for theorem 7.2a? Let me see what is we say in 7.2a. Yeah, this would be true as well a posteriori. But so first we just first demonstrate something a bit less, and now we get in a stronger conclusion. Yeah, but a posteriori it follows here that in fact we get equality there. All right, so let's return to this. I mean, this is we're almost done. So this is now just comparing it. We also have that di is less or equal than mi by theorem 7.2a, right? So look, we're in a situation, so you have a sum of finitely many positive integers. The sum of the di's is equal to the sum of the mi's. And each of the di's is less or equal than mi. So the only way this can happen is if di is equal to mi for all I. Right? So think about it for a second. If you have a sum of integers and another sum of integers, and these two sums are equal, but also you know that each summand here, every single summand here, is bounded by the corresponding summand here. So then the only way to achieve the maximal sum by this is if when each summand is equal to the corresponding summand here. Yeah. All right, so this is how we get that these numbers must actually be equal. So each di is equal to to the corresponding mi. All right, so this tells us all this information about about the generalized eigenspaces. All right. Yeah. So this is an analog, like I said, it's an analog of the theorem we had for the generalizable operators, where instead of generalized eigenspaces, we use regular eigenspaces. But now this is a more general result. And as you see, the proof was also more complicated this time. Okay, so next time we'll see also how all of this helps us with the Jordan canonical form and how it helps us to find Jordan canonical form for a given operator with a splitting characteristic polynomial. But I'm going to stop here for today. So thanks everyone for your attention. Yeah, I'm going to stop here. Thank you. All right, thanks everyone. Bye-bye.